the latest oscilloscope technology improvements. My name is Nicole Van Wert from Transcat, and I'll be your moderator this afternoon. Our presenter today is Mike Hoffman with Agilent. Mike has been a part of Agilent's Oscilloscopes and Protocol division for 2 years. In that time, he has been a product planner, application specialist, business developer, and all-around road warrior for the InfiniVision X-Series oscilloscope. Mike enjoys working directly with end users to help tailor Agilent's roadmap for the ever-changing landscape demanded by today's design and manufacturing challenges. Today we will spend the first part of our time in presentation, and we will end the call answering your questions. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that this webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to Mike.
Okay, thank you very much, Nicole. Hello, everybody. Welcome to today's webinar. Today we're going to focus on how oscilloscope technology has improved over the last about 10 or so years. The goal of today's webinar is first and foremost to inform you about the latest and greatest capabilities of these pretty integral pieces of test equipment. And by the end of today's session, I hope you walk away with some key pieces of information that will help you decide whether an investment in a new oscilloscope is prudent and how you can save time and money in the process. If you're on the market to upgrade to a new oscilloscope or are simply curious about the latest improvements in technology, this webcast is for you. This presentation will briefly address various oscilloscope consideration factors, and we will provide you with some formulas for determining required performance and some general recommendations on what we believe are important things to consider. We'll start with the banner specifications that everyone should be somewhat familiar with, and then also discuss some other factors that may not be on the top of your head, but I think are worth discussing. Let's begin. So, as you can imagine, oscilloscopes come in a variety of formats today. Handheld scopes are primarily used for field service. They're the most portable and have battery operation, but they also deliver the lowest performance and have limited feature sets. With PC-based oscilloscope modules, your computer provides the user interface. Although these types of scopes may provide the lowest cost, they also have limited performance, but they do provide easy connectivity to other waveform analysis tools, such as MATLAB. The most common type of oscilloscope is a portable benchtop scope with an embedded operating system, and these scopes are typically preferred for general-purpose troubleshooting. And then finally, all of today's highest performance scopes in terms of bandwidth and sample rate are generally Windows-based. And although these scopes typically provide the broadest range of advanced measurement capabilities and high performance, they're also the most expensive, and whether or not Windows is advantageous is debatable. First, let's talk about bandwidth. So in the days of analog signals, it was simple to determine how much bandwidth you required on your scope. But in today's digital designs, your clock speed does not determine the bandwidth required. Edge speed is a much more accurate way to determine your signal's effective bandwidth. All fast rising edges have an infinite spectrum of frequency components, but however, there is an inflection or knee in the frequency spectrum of fast edges where higher frequency components are pretty much insignificant. And for high-speed signals with rise time characteristics based on 10 to 90%, F knee is about 0.5 divided by the rise time of the signal you want to measure. The next step is to determine the required bandwidth of the oscilloscope to measure this signal. The table in this slide shows some multiplying factors for various degrees of accuracy for scopes with a Gaussian response, which is typical of a scope 1 gigahertz and below. Let's walk through a simple example. So if your fastest digital signals have a rise time of 1 nanosecond, then the maximum practical frequency component of the signal is 1/2 divided by that, or approximately 500 megahertz. Remember, this frequency has no relationship to the clock rate, just the edge speed. So for a fast rise time measurement, and you want accuracy in the range of 3%, the minimum scope bandwidth would be approximately 1 gigahertz. However, if you're able to tolerate, say, about a 20% timing error, when making measurements on your signals, then you could use a 500 megahertz oscilloscope. For example, a 1 nanosecond edge would be measured as 1.2 nanoseconds. So if your budget is limited and you can tolerate this degree of error, then a 500 megahertz scope may be the right choice for you. But if you want higher accuracy, then 1 gigahertz would be the right choice if it fits your budget. Next, let's talk about memory depth. So scopes with a deeper acquisition memory are of course able to capture longer waveforms while still sampling at a fast sample rate. And although intuitively you might think deeper is always better, there's often trade-offs involving deep memory. Using deep memory requires additional processing time, first and foremost, which means waveform update rates will be reduced, sometimes pretty significantly. And for this reason, most oscilloscopes on the market today have a manual memory depth selection that you have to select through a menu. And a typical default memory depth setting when you turn the box on is usually pretty shallow, say 10 to 100,000 points. And if you want to use the deep memory, you must manually turn it on and deal with that update rate trade-off I spoke about. This also means you must know when it's important to use deep memory and deal with and when it's not important in order to deal with the update rate trade-off. One big difference Agilent has is with our MegaZoom technology, where you don't have to be a scope expert and make this trade-off manually. It automatically selects deeper memory when it's needed in order to maintain fast waveform update rates. And with this custom technology, the scope always remains responsive, even when using deep memory. So again, let's walk through a quick example and determine how much memory depth is required for a particular measurement application. So to determine how much memory you need, the first step is to determine the sample rate you need. The sample rate is related to your bandwidth needs, which is again determined by the fastest rising edges in your designs. We recommend a rule of thumb of sampling 4 times faster than the bandwidth of the signal that you need. So in our example here, with our 500 megahertz signal, our required sample rate, as you can see here, is 2 gigasamples per second. The next step is to determine the longest time span of signals you need to capture and display. And then once you know these two things, determining the amount of memory you need is actually quite simple. Time span divided by sample interval, which is simply the inverse of the sample rate. So if I need 2 gigasamples per second and I need 2 seconds of time, simply multiply those two together and you get 4 million points of memory that is required. So what's our recommendation? Well, of course, select a scope that has sufficient acquisition memory to capture your most complex signals with the resolution you need to make accurate measurements. Additionally, there's some special modes that oscilloscopes offer. Agilent calls it segmented memory. You may also hear it called replay mode or panel mode, but it's a special mode that's available, and it essentially optimizes the acquisition memory by only capturing important segments of the input signals, essentially taking snapshots of the trigger condition each time it occurs. This is especially useful when there's a lot of idle time between signals. Examples of this would be a pulsed radar, laser bursts, or packetized serial packets, where there might be milliseconds of time in between events, and instead of the scope wasting its memory digitizing all of that idle time in between events, it only captures the actual packetized data itself. In this particular example, we're capturing 1,000 consecutive flex ray serial bus frames with a particular ID that we set up with a trigger, and with precise time tagging of each event, we can know the time between each frame. In this case, we captured 1,000. The 1,000th one occurred approximately 3 seconds after the first, and capturing a continuous time span this long would have required over 120 million points of conventional memory. But with segmented memory, we optimized it, and we're able to do it with only 4 megapoints of memory. An often overlooked specification of an oscilloscope that you should definitely consider is waveform update rate. So often when you're debugging a new design, you'll need to evaluate a signal's dynamic behavior. Examples of this would be jitter, noise, or random transients or rare glitches. There are 3 reasons why fast update rates are important in an oscilloscope. First, if an oscilloscope updates waveforms very slowly, it can make using the oscilloscope at all a very frustrating experience. Second, a fast waveform update can improve the display quality of the waveform that you view on the screen. But most importantly, fast waveform update rates can improve the scope's probability of capturing the random and infrequent events that may be keeping you up late at night. Oscilloscope dead time is the time it takes for a scope to process and then display an acquired waveform before rearming its triggering for the next acquisition. This time may be many orders of magnitude greater than the acquisition time on fast time per division settings. Dead time is essentially the inverse of the update rate. So the smaller the dead time, the faster the oscilloscope can update the screen. This is key to improving the probability of capturing a signal anomaly or glitch during the scope acquisition time. Here we show an example of capturing an infrequent glitch with the scope at two different update rates. The scope on the left is able to update at 1,000 waveforms per second. It may look and feel responsive, but when attempting to capture an event that is very infrequent, 1,000 waveforms per second may be statistically very low. In this example, the infrequent glitch occurs just 10 times per second, making the probability of capturing the glitch only 0.25% when observing the scope's display for 5 seconds. The scope on the right can update at 1 million waveforms per second. This scope has a 92% probability of capturing the same infrequent glitch within 5 seconds. A higher update rate gives you more confidence in your designs by plotting more information on the screen faster. Finally, let's talk about how waveform update rate can speed up mask or limit testing. Conventional oscilloscopes typically test about 10 to 60 waveforms per second using software-based algorithms. And at 60 waveforms per second, the update rate on the screen is fast enough to appear responsive to our eyes. But the time required to accumulate enough data to be statistically meaningful will take several minutes or possibly hours. In this example, an Agilent X-series oscilloscope on the right has tested 1.7 million waveforms in only 6.3 seconds for an average speed of 268,000 tests per second. A competitive scope on the left has tested 100 waveforms in 3 seconds for an average speed of 33 tests per second. On the left, enough samples for 6 sigma resolution, or roughly 300,000 waveforms, would take almost 3 hours. Agilent's Infinivision X-series oscilloscopes can accomplish this in 1.1 seconds. If your particular test setup has 10 signals that need to be probed and tested for 6 sigma quality, you would save more than 30 hours with our faster solution. If failures were found, these tests would need to be repeated, significantly multiplying the total time required to test for 6 sigma QA. Next, let's talk about channel count. As today's digital designs have become more and more complex, more channels of acquisition and display may be required, but there's a trade-off, and that is, of course, price. 2- and 4-channel scopes are very common today, but a 4-channel scope will cost you more than a 2-channel scope. And if you need more than 4 channels, your choices become very limited, and the price of an 8-channel oscilloscope can be extremely expensive. But there's another alternative, a mixed signal oscilloscope, sometimes called an MSO. MSOs combine all of the capabilities of oscilloscopes with some of the capabilities of a logic analyzer. Just think of it as having a few channels with high vertical resolution, typically 8 bits, plus several additional channels with very low vertical resolution of 1 bit. And although MSOs may lack the large number of digital channels of a logic analyzer, one of the primary advantages of an MSO is its familiar use model of an oscilloscope, which is usually considered to be easy to use because of familiarity. Our recommendation is to select a scope that has a sufficient number of channels of acquisition so you can perform critical time-correlated measurements between analog and digital inputs. Next is triggering. Triggering is often the least understood function of the scope, but it's one of the most important capabilities of the scope that you should understand, especially if you need to monitor very complex signals. You can think of oscilloscope triggering as synchronized picture taking. A photo finish of a horse race is analogous to oscilloscope triggering. To accurately record the finish of the race, the camera's shutter must be synchronized to when the lead horse's nose crosses the finish line in a forward direction. In this slide, we show a scope set up to trigger on rising edges of the input signal at +2 volts. In this case, we can see a rising edge of the input signal at exactly center screen. This is the scope's default trigger condition. Of course, every oscilloscope on the market can accomplish this. Some of today's oscilloscopes offer more advanced triggering modes in order to synchronize acquisitions on more complex signals. In this slide, we show an example of what's called a pattern trigger using a mixed signal oscilloscope, where we are defining a bus state on the digital lines to trigger on. In this slide, we show an example of a setup and hold time violation. In the screenshot on the left, the scope has been set up to trigger on a rising edge of a clock signal, which is channel 1 in yellow. In the screenshot on the right, we've set up the scope to uniquely trigger on just violation signals using the scope's setup and hold time trigger mode. In this case, we have set up the scope to trigger only if the setup time, which is the delta between the data's edge and the clock's edge, is less than 25 nanoseconds. Now the scope triggers and captures on just this condition, which in this case we consider a timing violation. Generally found on Windows-based oscilloscopes, visual triggering allows the user to create essentially a two-stage trigger. This is kind of the latest oscilloscope triggering technology that's hit the market in recent years. First, the scope will trigger on a user-defined hardware trigger condition, such as a rising edge trigger or a rise time trigger, and then qualifies the trigger by checking if it enters a user-defined zone on the screen. This can sometimes be helpful in isolating glitches or triggering on difficult signals that you can see on the screen but are difficult to parametrically calculate and create a trigger for. Now be aware that speed is generally highly impacted when using this feature on most scopes, as the zone qualification is done as a post-process in software. Update rates can drop to the range of dozens of updates per second. But one example, or one exception of this, would be the Agilent 4000X series, which accomplishes this qualification in hardware and keeps speed very high, over 200,000 updates per second still. The implementation is similar, but due to the hardware nature, the complexity of the zone setup is much more limited than you could accomplish in a post-processing software environment. So what I generally recommend is it would be a good idea to contact Transcat and get your hands on a loaner unit, and you can play with it yourself and determine if the feature is useful for you. So what do we recommend? Of course, select a scope that has the types of advanced triggering that you may need to help isolate waveform acquisitions in your most complex signals and designs. Sixth in line here is display quality. So looking for and finding subtle details of signals that may be buried within more complex signals requires a scope with what we call multiple levels of display intensity gradation. Now, intensity gradation effectively adds a third dimension to the displayed waveforms and gives the oscilloscope somewhat of an analog look and feel. In this slide, we show the capture and display of a complex modulated signal, in this case analog video, using three different scopes. On the left, we show how a traditional analog scope displays this complex signal. The display in the middle was taken with a digital storage oscilloscope, or DSO, a first-generation digital scope essentially, where there's no modulation whatsoever. The pixel on the screen is either on or off. And as you can see, you lose a lot of detail. The display on the right was taken from an Agilent Infinivision X series scope, which is able to display up to 64 levels of intensity gradation, or essentially the brightness of the pixels. And as you can see, with this scope, we have a much clearer picture of the dynamic analog nature of our input signal. In addition to evaluating the intensity modulation on the screen, other factors to consider are display size, display resolution, and whether or not the scope has a color display or a monochrome display. So what do we recommend? Select a scope that provides multiple levels of intensity gradation and also satisfies these other factors as you see fit. Next is serial bus applications. So most of today's digital designs include one or more different types of serial buses for communication between devices and subsystems. And it's often necessary to either verify proper bus communication or time correlate serial bus communications to other digital or analog signals in your design. Many of today's scopes have an optional built-in serial bus protocol and triggering capability. And if your designs include any of these serial buses, then selecting a scope that can decode and trigger on these buses could be a significant time saver to help you debug your designs faster. The screenshot in this slide shows what we call a time-correlated decode trace below the lister in blue, along with a lister display or event table showing the decode of multiple and consecutive packets and frames in a tabular format up at the top, much like a logic analyzer may. The lister table on Agilent X-Series oscilloscopes can be minimized, full-screened, or half-screened, and data can also be exported in a spreadsheet-style format, as opposed to just a screenshot. So what are some things to consider? Well, when selecting a scope that can provide serial bus triggering and decoding, there's a few factors you should think about, such as, obviously, which protocols are supported by the platform. Also think about, does the scope utilize software-based or hardware-based decoding? Software-based decoding that's done in post-processing can be slow, especially when using deep memory or while decoding multiple buses at the same time. It can also slow down the waveform update rate of the scope, making it difficult to capture infrequent glitches or, more importantly, errors on the bus. Hardware-based decoding is fast and can enhance the scope's probability of capturing infrequent communication errors, which are common in most of today's designs. And Agilent's InfiniVision X-Series oscilloscopes are actually the only scopes on the market today that utilize hardware-based decoding methods. The ASIC technology inherent to the scope is able to decode these in real time in hardware, so there's no delay or lag on the software side. Lastly, does the scope provide serial eye diagram mask testing for testing the signal integrity of some of today's higher speed differential buses? It's something to contact your manufacturer of choice and see what their options are. So what do we recommend? Selecting a scope that can trigger and decode serial protocols can help you decode and debug your designs much faster. No more bit counting. You know, that was a technique for quite some time. Now it's all automatic and inherent in the box. So choose accordingly. Next, measurement and analysis, which of course is one of the biggest advantages of today's oscilloscopes over old analog scope technology. You can now perform various measurements and analysis on the waveform intrinsically in the box. You'll find digital scopes from various vendors have a wide variety of measurement capabilities, and nearly all of today's scopes have manual cursor and marker measurement capabilities, as well as a minimum set of automatic pulse parameter measurements, such as rise time, fall time, frequency, pulse width, etc. As you move up in price and performance, you'll typically have more measurement and analysis tools at your disposal, such as mask testing or application-specific compliance testing. And although many advanced waveform math functions can be performed offline on a computer using software like MATLAB, having this capability embedded in the scope not only makes it easier to perform these types of advanced math functions, but also provides an updated display of waveform math functions in order to show dynamic signal behavior. In this slide, I'm showing 4 examples of different types of waveform analysis and measurements. In the first on the upper left, pulse parameter measurements with statistical analysis. Below that, pass-fail mask testing. On the upper right, we have FFT waveform math to look at spectral analysis. And on the bottom right, an application-specific compliance test where the scope provides automatic pass-fail information based on industry standards. In this case, we're looking at current harmonics on a power line. Next, number 9, is connectivity and documentation, which is obviously very important. And many of today's digital scopes are used in an automated test environment, both in R&D and especially on manufacturing floors. Automated testing requires the scope be connected to a computer via various possible connectivity ports. Most older scopes were limited to GPIB or HPIB, as you may know it, and RS-232 connectivity, and many people still use that today. But most of today's scopes and MSOs utilize USB or LAN connectivity. In addition, many of today's digital scopes have built-in web servers, making it easier for engineers across the globe to access scope measurements. They may reside in another part of the world. If you require your scope be used in an automated test environment, ensure the scope you select is fully programmable. In other words, make sure that any measurement that can be performed using the scope's front panel and menu controls can also be programmed remotely. Of course, all of Agilent's oscilloscopes are fully programmable. It's often important to document and save test results off an oscilloscope as well. One method of documenting test results is to simply dump a screen image to a printer connected directly to the scope. But a more common method of documenting test results today is to save data. In addition to being able to transfer data to a PC through USB or LAN, most of today's digital oscilloscopes have the ability to save images, waveform data, and serial decode data in various formats directly to a USB memory stick. Saved images and screenshots and waveform data can then be easily imported into word processors, spreadsheets, or software applications such as MATLAB for further offline analysis. Next is probing. So although we have listed probing as the number 10 thing to consider when selecting your next scope, it should be by no means considered the least important factor to consider. In fact, it may be the most important consideration. Your oscilloscope measurements can only be as good as what the probe delivers to the scope's BNC inputs, and if the probe loads the circuit under test and or distorts or changes the input signal, then your scope measurements will also be distorted and inaccurate. Good probes should not disturb the input signal and should be ideally delivering an exact duplicate of the signal that was present at the probe point before the probe was attached. Now, an important thing to remember is when you purchase a new scope, most of them ship with a standard set of high-impedance passive probes. These types of general-purpose passive probes are the most commonly used, but they have limited bandwidth. So if you're using a 500 megahertz probe on a 1 gigahertz scope, you've just turned your oscilloscope system into a 500 megahertz bandwidth measurement system. If you require higher bandwidth probing, you'll need to purchase a specialty probe for that, as well as any other specialty probing scenarios, such as high voltage, differential probing, current probing, etc. So what is our recommendation? Make sure to select a scope from a vendor that can also provide the variety of specialty probes that you may require. The last key issue is total cost of ownership. So if you're in the market to purchase a new scope, you probably have a fixed budget. And if the budget is too limited, then you'll have to make some trade-offs regarding features and performance you want, such as discussed earlier. So be willing to prioritize and select a scope that provides you with the highest value. And much like purchasing a new car, many people do not factor in the long-term costs of things like maintenance, repairs, or future upgrades when you're looking at test equipment. So let's look at a few different scenarios and how the newest scopes can help you save money in the long run. Maintenance can be a big cost factor over an extended product life cycle. Two big considerations in this arena are calibration costs and reliability. Now, Agilent's X-Series oscilloscopes use patented MegaZoom 4 ASIC technology. It's essentially an oscilloscope on a chip, and this allows us to utilize very low power electronics, since a powerful software processing chip is not required to acquire and plot waveforms. X-Series oscilloscopes actually only use roughly 100 watts and produce very little heat, and this provides huge benefits. The minimal heat puts less strain on the sensitive electronics inside, which allows us to have an industry-best 24-month calibration cycle, where most pieces of equipment you'll see 12-month calibration cycles. This reduced heat also extends the life of our products, and the X-Series oscilloscopes have exhibited mean time between failure rates of over 250,000 hours. This is equivalent to 8 hours of use every day, 7 days a week, for the next 85 years. Transcat can offer you fast turnaround times on oscilloscope calibration and also gives you a one-stop shop for hardware and future calibration needs. Additional cost considerations are probes and upgradability. Now, some oscilloscopes in the market offer fully upgradable bandwidth, upgradable digital channel or MSO capabilities, and upgradable software applications that can be purchased and installed after you make your initial hardware purchase. Now this is a huge savings for you. By offering upgradability to your existing hardware, you no longer have to purchase a whole new oscilloscope when your measurement needs change. If you're interested in learning more about oscilloscopes and oscilloscope measurements that are available, you can download these documents at no charge using the URL listed in this slide. Simply insert the publications number listed here in place of the X's on the URLs listed below. Alternatively, you can go to Agilent's website, which is just www.agilent.com, and then enter the publication number into our search engine box on the upper right. So here's kind of an overview of some of the products that were used in the screenshots today. We offer a broad range of performance capabilities and price points with dozens of models to choose from the 2000s X series, which is a great entry price for lower bandwidth needs, all the way up to the 4000 X series, which features that hardware-based zone triggering and up to 1.5 gigahertz of bandwidth. With that, I'd like to open up the presentation to any questions you may have, and thank you for your attention and attending today. If you have any questions, please feel free to use the chat window down below and make sure to address your question to all attendees so we can see that and address your questions. Thank you very much for attending.
Thanks, Mike. Okay, I'm going to go to our first question. And again, at any point in time, please send us a question in and we'll try to address it. First question. Why do you recommend a sampling rate of 4 times the bandwidth, and what does that mean?
Yeah, sure. So I mentioned that in some of the first slides as far as how much sample rate is required to capture certain bandwidths of signals. So according to Nyquist's theory, if you have a perfect band-limited signal, you need to sample at least twice the rate of that bandwidth. And that usually doesn't work out perfectly in practice, so we recommend doubling that and having a sample rate 4 times higher than the bandwidth. And anything higher than that, you see pretty diminishing gains. If you double your sample rate and go 8x over, you're not going to see a huge change in measurement accuracy. So 4x is a good rule of thumb. Anything more than that is nice, but not necessary.
Okay, the next one. How much does segmented mode extend memory by?
Sure. So actually it varies wildly depending on basically the duty cycle of your signals. So I've seen customers use segmented memory mode and such that they leave the oscilloscope running overnight to find events that happen once per hour or every few minutes. And you can essentially extend it out to infinity depending again on how frequent your trigger event is. So realistically speaking, it can at least usually double or triple your memory depth, and I've seen some extreme examples where segmented memory gives you the equivalent of terabytes of memory depth, which is, the deepest memory scope on the planet is 2 gigapoints of memory. So it starts getting into the realm of impossibility. So it really depends on your use model, but it can be extremely helpful almost all the time.
Okay. Third question. Why is your mask test mode so much faster than the other manufacturers?
Good question. So we do our mask testing in hardware. So that oscilloscope on a chip, that custom ASIC that we have designed, everything's done in real time as opposed to a software post-processing routine. So it increases the speed of almost everything we do across the board. Mask testing being definitely one of the biggest benefits for most customers who have to do some sort of QA or testing on products coming down the line, or simply just want to give themselves a reality check and see what their signals look like over an extended period of time or range of temperatures, things like that. So the reason it's so much faster is, again, due to that hardware ASIC we've designed that we base our architecture off.
Okay.
Good question.
I've got a couple more waiting. What kind of USB 2.0 support do your scopes offer?
Great question. So for low and full speed triggering, which is 1.0 and 1.1, we support that on the 4000 X series across all bandwidth points. So I guess the first way I'll answer that is USB 2.0 or USB in general is supported on our 4000 X series, low and full speed, trigger and decode on all bandwidths. And then for high speed, which is 480 megabits per second, we only support trigger and decode on the 1 and 1.5 gigahertz models, and that's due to the high bandwidth requirements. So USB 2.0 has a fundamental frequency of 240 megahertz. So to capture the third or fifth harmonic, you need at least a gigahertz or a gig and a half. So we can do high-speed USB 2.0 trigger and decode on the high-end models. We also have a suite of USB 2.0 compliance tests, signal quality tests available on our 1.5 gigahertz model, which allows you to do really cool things like histograms and an eye diagram mask test, as well as going through all the USB IF, USB 2.0 compliance tests, such as checking for rising edge speeds and jitter and things like that. So really nice suite of options available in our 4000X series.
Okay, great. One more. How can I analyze waveforms on my PC?
Great question. So we have a couple options for that. One, of course, is you can connect the oscilloscope to something like your PC and import the data into something like MATLAB or some sort of other post-processing software of your choice. Agilent does offer a few proprietary pieces of software that I think are really cool. One is called InfiniView, and it's basically a copy of an oscilloscope user interface on your computer. So you save the data off of your scope, import it into this program on your computer, and then you can manipulate it and document just like you're on an oscilloscope, but after the fact. And also we have something called Agilent Spectral Viewer, which allows you to kind of import the data and use it as a spectrum analysis tool. So you can go do waterfall diagrams and different things like constellation diagrams and things like that on it. So definitely the two Agilent tools I'd recommend, InfiniView and Agilent Spectrum Viewer, and then of course you have your traditional stuff such as MATLAB as well.
Thanks, Mike. Okay, unless there are any other questions, that concludes our time for today. So if you have further questions or would like to find out more about Transcat's product and service offerings, you can contact us at 1-800-828-1470. That's on Mike's final slide, or on the web at transcat.com. Or if you think of something you'd like to ask, you can email me directly, and I'll have Mike answer it for us at nvanwert@transcat.com. Thank you so much for joining us today, and we hope you found the information useful. Have a great week, everyone.